In today's video, I'm going to discuss displacement, time, and velocity time graphs, which are very common types of graphs used to describe rectilinear motion. So, we shall begin. We will begin with question number 1 by looking at this motion graph. This is what we call a displacement time graph. And we are going to consider that the body we are analyzing is moving in a straight line motion. So take a look at the displacement time graph that we have here. All right. So along the y-axis, of course, we have the position of the body, and along the x-axis, we have plotted the time elapsed expressed in second. Now, different segments of the graph are labeled here as segment A. Here it is, segment A, and segment B, segment C, as well as segment D. Okay, so specifically for segment A, the graph line starts at 0 time and at 0 position, and then it ends at the 10-meter position. For graph line B starts at the position of 10 meters. Okay, that's equivalent to 5 seconds. Okay, and ends at the -5 position mark. Okay, equivalent to 10 seconds. For graph line C, starts from 10 seconds up to 25 seconds, right? That is graph line C, a perfect horizontal graph line. And for the last segment, we have segment D, starts from 25 seconds to 30 seconds. All right. So this is our basis for answering the first question. Question number 1, which bit or bits of information can be gleaned from this type of motion graph? We need one or more answers. Okay, so letter A, position of a body at a given time. Letter B, instance when the body is moving. Letter C, instantaneous velocity of the body. Letter D, total distance traveled by the body. Alright, so do you know what the answer or answers are? Alright, correct answer are A, B, C, and D. So they're all correct. In other words, from a displacement time graph, we can determine all of these bits of information, right? So I'm going to explain why each one of this information can be determined from the displacement time graph. Alright, so we are going to explain now why determining the position of the body, alright, at any given time is possible by just looking at the displacement time graph. Okay, so we have here examples. Supposing that we want to determine the position of the body at a specific time, say for example, a time of 5 seconds. All right? So here is 5 seconds. Exactly at that time, 5 seconds, what do you think is the position, the body? So all we need to do is move up until we, all right, until we reach this part of the graph which corresponds to 10 meters. It's like asking, where is the body at exactly 5 seconds, right? So what we exactly did was to determine, based on the graph, okay, the segment A, or the blue graph line, which corresponds to the time 5 seconds. So what is its uh, corresponding position along the Y? You have there 10 meters. Another example, at time 10 seconds, what is the position of the body? So here is 10 seconds, and at this time 10 seconds, we would like to know what exactly is the value of the displacement, all right? And that is based on the second segment of the graph, the red graph line. Here it is. So at that specific time or instant of 10 seconds, what is the corresponding displacement or position? It is -5. And our last example is at time 30 seconds. So 30 seconds is the one at the extreme right. There it is. At time 30 seconds, what is the corresponding position of the body? So we move to the left and determine the corresponding value of the displacement. And here it is. Okay, at 30 seconds, we have uh, the equivalent value of the position, which is, of course, 0 meter. Okay. The second information that we can glean from a displacement time graph is the instance when we say that the body is moving. So, in the graph, there are three segments: segment A, segment B, segment C, and segment D. You will notice that only segment C shows a perfectly horizontal graph line, right? So, if the graph line in a displacement time graph is horizontal, the slope of that graph line is 0. So that indicates a zero slope means that the value of the velocity is also 0. In other words, uh, segment segment C represents that part of the motion of the body where it is not moving or it is at rest. That means graph line C will not be in our choices if you are answering the question at what instant or instance is the body moving. All right, but the other segments of the graph, graph A, graph line B, and graph line D, are not horizontal. Okay, that means each of these segments of the graph does not represent zero velocity. All right, let's start with what's given here from time 0 second to time 10 seconds. So 0 until time of 10 seconds involves the two segments, segment A as well as segment B. Okay? So, if we examine very carefully, graph line A is a straight graph line sloping upward to the right. The steepness or the slope of this graph line is constant because it's a straight graph line. It represents constant velocity. The velocity is positive because if you are going to get the delta D, the delta D, D final minus D initial is going to be positive. Meaning, if you're going to divide that by the corresponding delta time, we will get a positive velocity. But the magnitude of such velocity is constant. Okay? Now, how about graph line B? Graph line B is included in the time interval that we want, 0 to 10 seconds. Graph line B represents the motion of the body between 5 seconds and 10 seconds. Okay? But unlike graph line A, graph line B is sloping downward to the right. But then again, it is a straight graph line. Straight graph line suggests that the magnitude of the velocity, okay, the magnitude of the velocity does not increase nor decrease. It is constant all throughout from 5 seconds to 10 seconds. But is the direction of the velocity the same as that of graph line A? The answer is no. Okay? Because if you will notice, if you're going to get the slope, if you're going to get the slope of this graph line by getting the final velocity, or I should say final displacement, which is negative 5 meter, and then our initial is positive 10. So if you're going to get the delta D, okay, delta D, it's going to be negative 5 minus 10. And the answer is negative 15. The delta D is negative 15. Divide it by the corresponding time interval, which is 5 seconds. Okay, you are going to get, okay, a negative value or negative velocity. So you see, that is how a negative velocity in a displacement time graph looks like. It is sloping downward to the right. Okay? So, how about the last time interval, 25 seconds to 30 seconds? So that pertains to graph line D. Okay? Just like graph line A and graph line B, uh, graph line D is also a straight graph line, which suggests that the velocity that it represents is constant in magnitude. Okay, constant in magnitude, but is it positive or negative? All right, how do we know? Okay, let's get the change in displacement. Okay, so from time 25 seconds until 30 seconds, what is the corresponding final displacement at time 30 seconds? It is 0. And what is the initial displacement? It is negative 5. So when we get the delta D, okay, the delta D would be 0 minus, okay, 0 minus negative 5. The answer is positive 5 meter. And if you're going to divide it by the corresponding time interval, which is 5 seconds, we will get 5 meters divided by 5 seconds. And therefore, the velocity is positive 1 meter per second. Okay, positive meaning its direction is again going to the direction that we earlier mentioned, similar to what graph A represents. Okay, so if the direction initially was going east, all right, going east, graph line D also suggests that the direction of the motion of the body is also going east. So we were able to answer or prove that at this certain time interval, 0 to 10, as well as 25 seconds to 30 seconds, we say that the body is indeed in motion. It's only from 10 seconds to 25 seconds where the body is at rest. All right, the other information that we can also glean from looking at a displacement time graph is uh, the velocity at a particular time or instant. We call it instantaneous velocity. Okay, so for example, we want to find out, or you're asked, what do you think is the instantaneous velocity of the body at exactly 0 second? Okay, exactly at 0 second, what is the instantaneous velocity? The answer given here is Vn equals positive 2 meters per second. Right? Uh, to some people, when they uh, when they are told that the graph line, like segment A here, is touching the 0 meter mark and 0 time, okay, which is commonly known as the origin, okay, they say that the initial velocity is 0. But the fact is, it is not equal to 0. The reason is uh, the graph that represents the motion of the body from 0 time to 5 seconds here is actually a straight graph line. Okay? So, in a straight graph line, displacement time graph, the slope is constant. In other words, the velocity must also be constant. Okay? And if you're going to calculate for the velocity during this time interval, we can actually do it mentally. Okay? The formula is just get the change in displacement within that period of time. So let's try. What is the final displacement? It is 10 meters. What is the initial? It is 0 meter. So what is the change in displacement of the body as it moves from 0 to 10 meters? The answer is 10 meters minus 0. And then the time interval involved is from 0 second to 5 seconds. So you're just going to divide 10 meters divided by 5 seconds. So you will get 2 meters per second, and that is a positive instantaneous velocity. All right? The velocity that we're talking about here, or the velocity that we've just computed, involves time interval from 0 to 5 seconds. Right? So, in effect, we are actually describing average. The average velocity, okay, between 0 second and 5 seconds is equal to positive 2 meter per second. But that average velocity is naturally also equal to the instantaneous velocity at any given point within this straight graph, including at time 0. All right? Whatever is the average speed or velocity, average velocity from 0 to 5 seconds, okay, which is actually computed as positive 2 meter per second, that also represents the instantaneous velocity at any given point within this graph line. All right? So that is how we determine instantaneous velocity. Uh, not anymore shown, but for example, you want to find out what is the instantaneous velocity at this particular instant. Okay, here. Okay, do you see this graph line B? That point in the graph, which has an equivalent displacement of 0 meter, but the corresponding time, as we have estimated earlier, is about what? 7 seconds. All right? So at exactly 7 seconds, how will you be able to find out what the instantaneous velocity is at exactly 7 seconds? Okay, so all you have to do is just determine the slope of this graph. Okay, the graph line, the whole graph line, colored red. Whatever comes out as your average, okay, average velocity will also represent the instantaneous velocity at that particular instant of 7 seconds. Now, for graph line C, if you're asked what is the instantaneous velocity at exactly 15 seconds, all right, it is here at this point. Since the whole graph line C is horizontal, okay, the average velocity within that time interval, since it is horizontal, we say is 0. All right? Any point within this graph line corresponds to a 0 instantaneous velocity. Okay, the last information that we have mentioned earlier is the total distance traveled from a given instant or time interval. For example, you want to know what is the total distance traveled from 0 to 30 seconds. Okay, 0 to 30 seconds. So in your graph, that corresponds to uh, at this point 0 time or 0 second up to 30 seconds. So we're talking about the whole journey or the whole motion that's represented in this displacement time graph, 0 up to 30 seconds. So how do we determine the total distance traveled by the body? All right. Uh, you must remember that total distance is simply referring to the total path taken by the body without considering the direction. All right. Regardless of the direction, okay, we simply add all of the lengths corresponding to each time interval. So for example, it says here total distance is just the sum of 10 meters plus 15 meters plus 5 meters. Okay, where is this 10 meters? All right, it's like this. From time 0, okay, until 5 seconds, okay, what is the displacement of the body? So there's nothing to compute because all you need to do is read it directly from the graph. All right? From 0 to 5, how far is the body from the origin? The answer is 10 meters. So if you're talking about distance, okay, it answers the question how far. 10 meters is the distance traveled at the end of 5 seconds. Okay? Then, what happens from 5 seconds up to 10 seconds? So that is represented again by graph line or segment B. Okay? Since we ignore the direction of travel, whether it is positive or negative, it doesn't matter. So this is how we just determine how far has the body moved, okay, between 5 seconds until 10 seconds, okay? So from 5 up to, what's this? About 8 seconds, all right? Isn't it that the body has traveled also a distance of 10 meters, right? 10 back to the origin. So that's a total of 10 meters, right? And then the remaining part of the graph, segment B, from 8 seconds to 10 seconds, we are given that the position is -5. So we ignore the sign. We just take the magnitude of -5 meter, which is 5. Then we add 10 meters plus 5 meters, a total of 15 meters. All right? So the total distance traveled by the body between 5 seconds and 10 seconds is actually 15 meters. Now, from 10 seconds to 25 seconds, represented here by graph line C, the body is not in motion. All right? We mentioned that already earlier. For a graph line that is perfectly horizontal, the slope is 0 and therefore no velocity. It is equal to 0. The body is motionless. So that leaves us only with the remaining graph line D, meaning from 25 seconds to 30 seconds. Let's count. It starts from -5 back to 0, disregarding the sign of the position. Okay, when you walk 5 meters back to 0, it means you are able to walk a distance of 5 meters. So we have here 5 meters for a total of 10 meters plus 15 meters plus 5, or a total of 30 meters. All right. Now, equally important also, although it was not mentioned, okay, it was not mentioned in our answer earlier. If we can determine the distance traveled from a displacement time graph, okay, we can actually also determine the total displacement. Okay, in the first place, the graph line is a displacement time graph by itself. So there's no reason why we cannot determine the total displacement. So for example, what is the total displacement of the whole journey from 0 second up to 30 seconds? Okay, displacement refers to the distance or the length of the path taken from the initial to the final, right? And mathematically, or the formula is simply getting the difference between the final position minus the initial position. What is the final position? Isn't it 0? Okay, 0 is the final position. What is the initial position? It's also 0. Okay, it is as if the body has not been displaced. You see, that is the what do you call this? The unique characteristic of the concept of displacement. It's really different from how we understand distance, right? If the distance total is 30 meters, here the total displacement is 0. All right. So both total distance as well as total displacement, or it, it may also mean just the distance traveled within a certain time interval. It doesn't have to be the whole journey. Okay, so those sort of information pertaining to distance traveled and displacement within a time interval can also be determined from a displacement time graph. We are done interpreting displacement time graph. So our next type of motion graph is what we call the velocity time graph. We have here an example of a velocity time graph. We know that it's a velocity time graph because, for one thing, the variable shown along the y-axis represents velocity. There's supposed to be an arrow here, all right? And another thing, There are values for velocity that are in fact plotted along the negative y-axis, all right, such as negative 5 meter per second and negative 10 meter per second. If this were a speed versus time graph, okay, where there's no such thing as negative speed, this will not be how a speed time graph should look like. There should be no negative values for the speed, okay? So that's one misconception that you have to check. A speed time graph is so much different from a velocity time graph. What we have here is a velocity time graph because we are treating this quantity, velocity, uh, as a vector quantity. It has magnitude and a specific direction. Okay, speed is not a vector quantity; it's a scalar. So there is no such thing as negative speed. Okay, to some people, they interchange a speed versus time graph. Okay, it's just the same as a velocity time graph. The truth is they are not. Right. The question here actually is for you to determine which among the given statements, which I'm going to show to you later, which of those statements is considered false statement, no? Regarding the motion of the body as depicted in this velocity time graph. All right? So let's start first analyzing and interpreting each segment of the graph labeled here as A, B, C, and D. Take note, this looks like what we had earlier for displacement time graph. Okay, but we are actually now on analyzing velocity time graph. All right, I hope that is clear. So let's begin with graph line A. Obviously, graph line A is not a straight graph line, right? But it is a curve A. So at this early, may I emphasize that the slope of any particular graph or graph line or curve in a velocity time graph, okay, the slope of the graph represents acceleration, which is also a vector quantity, right? That is the slope of a velocity time graph. It represents acceleration, both the magnitude as well as the direction of the acceleration can be determined if you're going to analyze velocity time graph. Let's begin with graph line A. Okay, so it's not straight. It's not the typical graph line that we have seen earlier. But uh, aside from saying that the slope is not constant, in fact, this shows a decreasing value for the slope. In other words, this suggests that the acceleration, okay, the magnitude of the acceleration is decreasing in value. All right, decreasing in value for the acceleration. How about the direction of that acceleration? We know that the magnitude is decreasing, but how about the direction? All right, to get the direction of the acceleration, okay, we just check what will be the sign that will come out if we are going to divide delta V over delta T. Getting the delta V is subtracting the final V. Okay, supposing here is the point in the graph that corresponds to the final velocity, and that means it is positive 10 meters per second. All right. Then the initial, let it be understood that the initial velocity occurs at 0 time. All right. So what is delta V? It is final minus initial. 10 meter per second minus 0. We have a delta V that is positive. You divide that by the change in time, which is equal to 10. All right. Our slope of the graph becomes positive. So we have a case where the motion is accelerating, but the velocity changes in magnitude is not constant, right? It's not constant. In fact, it is changing or decreasing. Huh? The magnitude of the velocity is decreasing. Take note, I didn't say that the velocity is decreasing. What I'm saying is the magnitude of the acceleration is the one that is decreasing. All right. So does that mean that the body is decelerating? Okay, careful. When we say decelerating, we are referring to a decreasing magnitude of velocity. So that's not what we mean here by decreasing acceleration. I hope that's clear. Now, if you're going to determine the magnitude, okay, of the acceleration in a graph that is not straight, okay, technically, what we should do, because I just said earlier that the magnitude of the acceleration is not constant. For example, you want to know the uh, magnitude of the acceleration at exactly 0 time. Okay, so the process is quite tedious because it will require you mathematically. The process is by applying what you call derivative, right? What is the value of the acceleration at that particular instant. Okay, we are not talking about time interval, but rather we are talking about at an exact value of time or instant. So the usual process of getting the slope delta v over delta t uh, can only be used if we will assume that the graph is straight. Okay, but since it's a curve, what we should do, in fact, is, for example, you want to know the instantaneous acceleration at this point here. Look at the cursor. Okay, at that point, that's about what? A little below 2.5 seconds. No? All right. At that instant, we can determine the acceleration graphically, that is, by drawing a line tangent to that point. Okay. So when you have a line tangent to that point, that means the line touches only a particular point in the curve, which corresponds to that particular instant. And then, from the tangent line, we can determine the delta V and the delta T, where we can now start computing for the slope. Okay, whatever the value of the slope that will come out will represent the instantaneous acceleration at that particular instant. Likewise, for any other point within the curve, the, the process is using a tangent line, okay, tangent to any particular point. So it's quite tedious, but I'm sure when you were discussing graphical analysis in your first lessons in kinematics, you probably are familiar with what I am trying to say. So we will just assume, for example, what is the average? Yeah, no? We have to be specific. If you want to know the acceleration from 0 time to 10 seconds, okay, we just talk about average acceleration, meaning it is the average of the individual instantaneous acceleration, okay, at any particular time. At first, at this point, 0 time, we can say that the acceleration is very high. So as time passes, we can imagine that the acceleration keeps on decreasing in magnitude. All right. So the graph line doesn't show a portion where the line is becoming horizontal. It's just that from a high value of acceleration, it keeps on decreasing in value or in magnitude. And then if you're going to take the average of all those instantaneous acceleration, okay, we will arrive at a value that is determined by using the usual formula delta v over delta t. All right? But that is what we call the average acceleration within the time interval 0 to 10 seconds. Okay. Let's move on to graph line B. For graph line B, obviously it's a straight graph line at sloping downward to the right. So this means that the slope of this graph line is not constant, or the acceleration that it represents is not what do you call this, is constant. Okay, did I say that the slope is not constant? Okay, I stand corrected. The slope for this particular graph line is constant. It doesn't change. All right, so it follows that the acceleration that graph line B represents is a constant acceleration. Okay, the same value all throughout from 10 seconds to 15 seconds. The value of the acceleration or the magnitude remains the same. Okay, but what is its direction? Is it positive or negative? Okay, so how do we know, or how do we determine whether it's positive or negative? We again apply the formula of getting the delta v, or change in velocity. What is the final velocity? Okay, at 15 seconds, it's here, negative 5 meters per second. And what is the initial velocity at 10 seconds? It's there, positive 10 meters per second. So getting the delta v, we just subtract negative 5 meter per second minus positive 10 meter per second. So we get negative 15 meters per second as our delta v. And divide that by the time duration, or 15 minus 10 seconds, which is 5 seconds. So negative 15 meters per second divided by 5 seconds, of course, you will get negative 3 meters per second as our acceleration of the body during this period of time. Okay, negative 3 meters per second. The magnitude is constant all throughout. But what is the meaning of the negative sign? Okay, the negative sign of our acceleration all throughout this graph line, it is negative 3 meters per second squared. Okay, now let's see. From 10 seconds up to, what's this? 13 seconds. 10 to 13 seconds. That's the time interval, okay, involved during this, or that corresponds to this first part of the graph line, segment B. Okay, the time interval is about what? 3 seconds. 13 minus 10, that's 3 seconds. Where we have a negative acceleration. Okay, what does it suggest about the magnitude of the velocity? Okay, from here, that's the initial velocity, 10. So as the time moves from 10 seconds to 13 seconds, what is happening to the magnitude of the velocity? It is in fact decreasing from 10 to 0. And that is usually what we call deceleration. The body is slowing down. All right, the body is slowing down. Its magnitude of velocity is decreasing until it becomes 0. We are talking about the velocity 0, which means that the body has instantaneously come to stop. Okay, but that is very instantaneous. At that particular point in the graph, we have a 0 velocity. Then from there, okay, as we continue, meaning from 13 seconds to 15 seconds, what is happening to the motion of the body? Okay, it starts from 0 velocity, then it increases in magnitude of velocity from 0 exactly at 15 seconds, the velocity becomes negative 5 meters per second. So that's obviously an increase in the magnitude of the velocity within a time of what? 2 seconds. In other words, we can safely say that the body is speeding up, right? Speeding up from 0 meter per second up to 5 meters per second. But the direction, okay, the direction of the motion, okay, the direction of the motion is now going to the negative direction, all right? Since all the values or all the signs of our velocity below zero, such as negative 5, negative 10, and so on, indicate that the velocity uh, is in the negative direction. If the motion being described is along the x, so we say it's going to the negative x-axis, okay? But if the path, the motion of the body is vertical, negative velocity would mean it's going downwards along the negative y. So you see, there are two kinds of motion involved or represented by graph line B. The first one is decreasing in the magnitude of the velocity, which we normally describe as deceleration, all right? And that corresponds to a negative acceleration. In short, the meaning of the negative acceleration is only that the magnitude of the velocity is decreasing, all right? Or in terms of speed, we say that the speed is uh, also decreasing, okay? The motion of the body is that it is slowing down, negative acceleration. But for the time interval, 13 seconds to 15 seconds, within the last 2 seconds, we have a negative acceleration. But the meaning of the negative acceleration is not the same as what we have here. Okay? The meaning of the negative acceleration here doesn't mean that the body is slowing down. No, it's not. It is in fact speeding up. Okay? Speeding up, but in the opposite direction, opposite to what it had here earlier. All right? So is the difference between speeding up and slowing down with the same sign of acceleration clear to you? I hope it is. Okay? Because there's a common notion that whenever the acceleration is negative, people would tend to conclude that the acceleration or the direction of the motion is negative. All right? So, not always, as I have explained here. So, let's proceed analyzing graph line C. Obviously, graph line C is perfectly horizontal. So, that means its slope is 0 or the acceleration is 0, which also means that the velocity at the initial time of 15 seconds, which is negative 5 meter per second, actually has not changed as the time becomes 20 seconds. So within the time of 5 seconds, the body actually has not changed its velocity. It remains negative 5 meter per second, okay, where the delta V is 0. So the acceleration is 0, okay? And finally, for graph line D, what do we have? We have a variable slope, okay, a changing slope, meaning the acceleration is not constant. Okay, it's not constant, but is it increasing in magnitude or decreasing? Earlier here, segment A, okay, we talk about decreasing magnitude of acceleration. But in here, segment D, we have the opposite. Okay, we have the opposite. That means the magnitude of the acceleration from 20 seconds to 30 seconds is increasing in magnitude. Okay, what do you think is probably the acceleration at the at exactly 20 seconds. All right. So just like what I mentioned earlier, we can use the method of drawing a tangent line. Getting the slope of the tangent line will tell you what the value of the acceleration at that particular instant. If you are going to consider graph line D, all right? But we will not do that. So we'll just say that the acceleration, the value of the acceleration, the magnitude of the acceleration that is represented by graph line D is increasing in magnitude. But what about the sign of the acceleration? Okay, how do you know again? How do you determine the sign of the acceleration? Of course, we do the usual uh, method determining the delta v. What is the delta v? It's the final minus the initial velocity. And at 30 seconds, what is the value of the speed velocity? It is 0. Okay? 0 as our final velocity at time 30 seconds. What is the initial? The initial velocity is negative 5. All right? Negative 5 meter per second. So if we get the difference, 0 minus negative 5, we get a positive value for delta V, which is positive 5 meter per second. And if we divide that by the time interval of 10 seconds, from 20 to 30 seconds, okay, our delta T is 10. So if we divide 5 meters per second divided by 10, we should get positive 0.5. Okay, that's the value of our uh, acceleration average. All right, on the average. Okay, that is not uh, the instantaneous acceleration, say for example at 20 seconds. No, it's not equal to negative 0.5 meter per second squared. Neither is it the instantaneous acceleration at time 30 seconds. All right, but most probably it is the instantaneous acceleration at the middle, at the point that is the middle point of this curve graph. All right, that's uh, that's just an approximation. Okay, it is, or it represents the average acceleration of the body at that particular point. Okay, representing a particular instant. Okay, we cannot exactly pinpoint now what is the middle point of this graph. All right, so the best that we can say is that negative, oh no, that positive 0.5 meter per second squared acceleration is just the average acceleration of the body, okay, represented by graph line D. All right, so I hope you were able to understand the meaning of each of these segments in the velocity time graph, because we will now look at the different statements that the question would like you to look at and identify which among those four statements is considered false. I hope you will be using our interpretation for the different segments A, B, C, and D in answering that question. All right, so the statements given in the options are letter A. Okay, segment A says here, segment A, increasing positive acceleration. Okay, is that correct or not? Segment A. Letter B. Segment B, does it represent a constant negative acceleration? Constant negative acceleration for segment B. And for option C, is segment C Okay, in segment C, does it mean that the what do you call this? That we have a constant negative velocity. Okay, segment C, constant negative velocity. And finally, option D says that segment D has decreasing negative velocity. Okay, so which among these options is considered false? Okay, use our earlier discussion. If you have if you were very attentive in our in my presentation earlier, okay, I'm sure you'll be able to get or spot the statement that is not correct. So which is it? Our answer is letter A. Why? Increasing. Does the steepness of the graph line suggest an increasing value for the slope? All right. It is positive because all the values for velocities here above zero are positive. Okay. It is the word increasing that makes this option incorrect or false. The word increasing. All right. All the rest, like in option B, option C, option D, they are all true statements as I have explained earlier. Okay. Again, using the velocity time graph, we have the third question. What is the acceleration of the body in segment B of the graph? All right. So this is just actually a review of what I have already presented, okay, earlier. But just to show you how we can determine the acceleration, okay, based from the graph, and we are referring to graph line B, okay. So the solution is something like this. We get the slope for graph line B, which is a straight graph line. Okay, the formula is delta V. All right, we have it. Delta V, or change in velocity, divided by change in time. Take note, we are referring to graph line or segment B. So the final velocity, okay, the final velocity is -5. Okay, that's exactly at 15 seconds. Now, the initial velocity corresponding to 10 seconds is 10 meters per second. So we get -5 minus 10. Okay, the delta V, of course, is -15 meters per second. And the time interval here is equivalent to 5 seconds. That is 15 seconds minus 10. Okay, so overall, what we get is a negative acceleration, -3 meters per second squared. So that was quite quick and easy, isn't it? In question number 4, we are asked to find the total distance during the time interval 10 seconds to 20 seconds based in the given velocity time graph. Okay, so how do we get this total distance for a time interval of 10 seconds to 20 seconds? You will notice that during this time interval of 10 seconds to 20 seconds, the segments of the graphs involved here are segments B as well as segments C. So, based on these graph lines represented by segment B and segment C, we simply find the distance, okay, traveled during this time interval, and the method that we are going to use here, the graphical method, is simply determining the area that is bounded, okay, by the graph line B. Okay, the area bounded by the graph line and the time axis. So we are actually referring to this space or area here as represented by uh, a shade colored red. All right. So it looks like that the area is a right triangle. That goes through also for the remaining time. Okay, that's approximately from 13 seconds to 15 seconds time interval. Okay, that area which we're also going to shade. Okay, again, it appears to be a right triangle. So if you're going to determine the two areas of the two triangles, that would represent the area that is traveled by the body, okay, during the time interval 10 seconds to 15 seconds. So let's determine now the area of the bigger triangle as well as the area of the smaller triangle. Okay, so from what we know in geometry, to find the area of a right triangle, we simply multiply the height of the triangle times the base and then divide them by 2. All right, so substituting in that the area formula of a triangle, we have 1/2 times 10 meters per second. What is this 10 meters per second? This is the height of the bigger triangle, which corresponds to the uh, velocity change from 0 to 10 meters per second. So we plug it here in the formula 10 meters per second. And what about the base of the bigger triangle? It represents the time interval from 10 seconds to about 13 seconds. So that's equivalent to delta t of 3 seconds. Okay? And then for the smaller triangle, the same method, 1/2 base times height. Alright? 5 meters per second here refers to the height of the smaller triangle. As you can see, this is the height. And that corresponds to delta V of 5 meters per second. We disregard the sign of the velocity since we are looking actually for the distance traveled. And therefore, what we have here is 5 meter per second, okay, ignoring the negative sign. Where did we get the 2 second? The 2 second refers to the base of the smaller triangle. Okay, from 13 seconds to 15 seconds, the difference is 2 seconds. Alright, so if you do your algebra, we will get this result. 15 meters is the area bounded by the bigger triangle. And then for the smaller triangle, okay, the area is 5 meters for a total of 20 meters. And this 20 meters represents the distance covered by the moving body within that time interval 10 seconds to uh, 15 seconds. That's just for the time interval 10 to 15 seconds. And we will also be determining the remaining time interval from 15 seconds to 20 seconds because the question is asking for that time interval 10 seconds to 20 seconds. So we will see in the next slide how we are going to proceed. Now, to determine the distance traveled by the body from 15 seconds to 20 seconds, that's represented by graph line C. Using the same method that we did for the time interval 10 seconds to 15 seconds, we also use the graphical method which is determining the area that's bounded by the graph line and the time axis. All right? So we are referring to this area. Okay, here's the graph line C and the area that it bounds with the time axis, which if we're going to shade it, all right, there it is. The green shaded area looks like a square or a rectangle. Okay, and how do we determine the area of a square? Isn't it that we simply multiply the two sides? If it is a square, just multiply one side by the other side. All right. Uh, for the side that is along the vertical, okay, representing the change in velocity, that's equivalent to 5 meters per second. Okay, just like earlier, we disregard the sign of our velocity change because, again, we are just determining the distance and not the displacement. All right. Now, what is the time interval involved here? Of course, the other side, which corresponds to the time interval from 15 to 20 seconds, and that is 5 seconds. So, multiplying 5 meters per second by 5 seconds, of course, we get 25 meters. So, this is the distance traveled by the body during that time interval of 15 seconds to 20 seconds. So what do we do next? Of course, we just add the two distances during the time of 10 seconds to 15 seconds, which we got earlier. It's 20 meters. And for the last portion, okay, of the time interval, the area bounded by the square, which is 25 meters, and the total is 45 meters. That's the final answer to the question, what is the total distance during the time interval 20 seconds to 20 seconds? Okay, so before we proceed to the next question, please take a look at the method that we did here. Okay, if it's your first time to hear the method, the graphical method of determining the distance traveled based on a velocity time graph, okay, especially in the case of graph line B, there is a possibility, all right, for you to shade this portion of the graph, all right. Look at the cursor. I am now showing to you this portion of the graph line, which I did not shade. Why? Because the area that we are supposed to shade must be, right, must be the area bounded by the graph line, all right. And for the smaller triangle, we actually mean that particular portion of the graph, okay, this one here, all right. So just be careful in doing your shading. Always remember, we are after the area that is bounded by the graph line with the time axis. All right? In the case of determining the displacement of the body during a time interval, all right, in this case from 10 seconds to 20 seconds, just like what we followed earlier when we tried to find distance traveled. All right, so displacement, as we all know, is a vector quantity requiring specification not only of the magnitude but also the direction. Okay, so using still the same method that we followed earlier, right? So let's have a look at the way we determine the area, okay? The area bounded by the graph line B, okay? Here is that graph line B, all right? From 10 meters per second, sloping downward up to this part, corresponding to negative 5 meter per second velocity, okay? Or within a time interval 10 seconds to 15 seconds, okay? So, uh, for the time interval 10 seconds to 13 seconds, the area bounded by the graph line with the time axis, as shown here by the bigger triangle, okay? Take a look at that. And for the remaining time interval, which is about 2 seconds, a total of 5 seconds, notice that I stated earlier, we are not supposed to uh, shade this part of the graph line. Why? Because this has been considered already when we try to determine the area bounded by the graph line with the time axis. Okay, we already used that portion of the time interval which we approximated to be 3 seconds. Alright, so for the remaining time interval of 2 seconds, what is the base of the smaller triangle here? It's only 2 seconds. Okay, so if we add the two bases of the bigger triangle plus the base of the smaller triangle, that corresponds actually to the total time interval from 10 seconds to 15 seconds, which is 5 seconds. Okay, now, the only difference in determining the displacement during this time interval, if you notice in our solution, okay, if for the distance earlier, we did not consider the sign, all right, the sign of our velocity, this time around, as you can see here, okay, we use negative 5 meter per second because, why is that so? Because the height of the smaller triangle, all right, the height of the smaller triangle actually corresponds to the change in velocity, okay, from 0 to negative 5 meter per second. And if we get the delta V, which is negative 5 minus 0, the delta V, which represents the height of the small triangle, is also negative 5 meter per second. And we will not disregard the sign. So the negative sign is written here so that when we do our algebra, we actually get 15 meters. That's the area bounded by the graph line during the time of 10 seconds to 13 seconds. Okay, a time interval of 3 seconds. And what we got was 15 meters. Okay, for that portion, the small triangle, okay, that the area bounded by the remaining graph line B is in fact negative 5 meters. So for a total of 15 meters minus 5 meters, and that is positive 10 meters. This is what we call the displacement from 10 seconds to 15 seconds. Okay, and of course we still have the remaining 5-second interval, okay, meaning the displacement of the body that's represented by graph line C, which is coming now in the next slide. We are now down to our last portion of our discussion, and that is determining the displacement, the remaining displacement, or that is represented by graph line C. So just like earlier, okay, we shade that portion. Again, it's a square, so simply we just multiply the two sides. Negative 5 meter per second here refers to the change in the velocity from 0 to negative 5. And the other side, of course, represents the time interval from 15 seconds to 20 seconds. Okay, so multiplying them, because this is a square, and the area of a square, as shaded here, is simply the product of the two sides. And negative 5 meter per second multiplied by 5 seconds, of course, we get negative 25 meters. So that is the displacement that's represented by graph line C. So all in all, what do we get for our total displacement? We just add uh, what we got earlier, which is 10 meters displacement, that's for the time interval 10 seconds to 15 seconds. And what we got here now for the graph line C, which is negative 25 meters, and adding them, we get finally the total displacement between the time interval 10 seconds to 20 seconds, which is negative 15 meters. So we are done. Thank you very much.